as the slides show, the point of this talk is really to evaluate exactly how well do large language models like GPT-4 do on predictive tasks. So these are tasks that, are like classification and things, which these large language models can do in this zero-shot way through in-context learning, but exactly how good are they, and how much labor are you actually saving if you do it this way, and the general sort of comparison around that. So I said on the title specifically GPT-4, the actual experiments through this mostly use GPT-3 from the literature, and then we've done some other experiments with GPT-3 and then some experiments with Cloud 2. There's reasons actually GPT-4 is a little bit difficult to do these experiments with. And then also for BERT-sized, there's some variation around that as well, but I'll start talking you through this. So also, before I get into this, I want to say that I'm not at my exact 100% best today. We had quite a difficulty with our flights. They took our carry-on baggage at the gate, and then we arrived with like nothing but our clothes. So we took the opportunity to actually use this as a little Gen AI demo to sort of warm up into this, and generated some cartoons of like, this terrible scene of like our baggage being snatched from us with my co-founder Ines, who you can also talk to after this about Spacey and Prodigy together. So one of the other reasons that I wanted to put a little bit of generative AI things into this is that through this talk, I'm actually going to show you some results where GPT-4 is doing pretty unimpressive at seemingly simple tasks. And I feel like in this and in many other things, there's only a sort of few takes available or few positions available on complex issues online. And one of the takes that's available on LLMs is a sort of generic LLM skepticism. And, people saying, well, actually, these things aren't very good. They're just stochastic parrots, etc. And I feel that this rings hollow to anybody who's actually using these things. And so I wanted to sort of put this in here and say like, well, no, like you, I'm using these things in my sort of daily workflows. So there's just a couple of questions where I'm, examples of the sorts of things I'm asking in my development workflow. And you can see from these really impressive language understanding capabilities, and then also general problem manipulation and problem solving abilities that go, I think, even beyond things like question answering. So it's like, pasting in an error and saying, how should I debug this, and getting quite reasonable responses is something that's like really characteristically different from these models than we were getting from language technologies before. And I think that's, it's really important to point that out and to keep that in mind, even while we switch over into thinking through these sort of simpler predictive tasks and trying to understand how these models actually perform in those tasks and why it might not be as easy as it seems. So as a little bit of background on me, I've been working in the field for a long time. Our open source library Spacey was first released in 2015. It's since had like a huge number of downloads, and it's really in use in thousands of companies. So it's quite a standard library for doing things like, recognition of companies, recognition of people, splitting texts up into tokens, grammatical analysis. It's known for both efficiency and sort of ergonomics in developer experience. So the API has been stable a long time, and one of the benefits of that actually is that ChatGPT is very good at producing Spacey code. So one of the things that we actually want to do much more of is make use of this, and especially for pattern mining and this type of thing. And then another tool that's we're well known for at Explosion is our annotation tool Prodigy. So this is a tool that you can easily script to queue up examples for annotation and really deconstruct annotation tasks in different ways to get the most out of the human time. So it's very flexible in this way, and I'll point to a little bit later some of the reasons for that flexibility and what the implications of it are in the presence of things like large language models. So here you see an example of little Python scripts that you can write to queue up examples and then pass them through and start a web server to queue up the annotations. So the idea here is to have an annotation workflow that scales down to even yourself or a few users, so that you can make use of the human signal in your annotations. And then finally, we've got our upcoming product, Prodigy Teams, which is this cloud and collaborative version of Prodigy. So we're very excited to have this coming out. And if you've been using Prodigy or you're interested in this, definitely check it out and sign up for the beta. All right, so on with enough of the preambles. I want to give you a bit more of the sort of overview of the talk. So there's really 3 points through this. One of the points that the case kind of rests on, or the premise of the talk, is that predictive tasks still matter. So these are tasks which are not generative, so you're not producing free-form output. Instead, you're producing some sort of structured output. And I'll show you a little bit more about exactly what that means. And then another premise of this is that in-context learning, so prompting LLMs, is actually not very optimal for predictive tasks, and in fact, given the current approaches and current models, performs surprisingly poorly on most of these tasks. So I'll show you a number of results from the literature and a limited range of experiments that we've produced for this to go through this, and then some reasoning for that. And then finally, I want to give some conceptual model and also workflow suggestions for what this actually means. So assuming that you want to do these predictive tasks and you recognize that, like, okay, just prompting an LLM isn't optimal, well, how can we actually make use of this breakthrough in language understanding to get better predictive models? So the overview here is, for this first point, is that generative models complement predictive models rather than replacing them. It's a different type of need and a different type of application context, so they're not like sort of fighting. You need both. So here by generative, I mean these types of like single or multi-document summarization, reasoning, problem solving, paraphrasing, style transfer, question answering. And over on the predictive side, these are things where you're producing one or more fixed labels. So you're producing something that you could describe with a schema. So something like text classification or entity recognition, extracting relations, semantic parsing, etc. Why do these predictive tasks still matter, even though we can do much more ambitious things with generative? Well, here's a little example of the types of information extraction that we might want to do. So here we're saying, okay, there's just some statement about funding announcement, and we want to extract this and put it in a database. So we can ask from this, why do we want to put it in a database? Why can't we just have, all of these things as text and then ask questions of that text? So that is like a different application experience that's now possible that wasn't possible before. So large language models make this possible, and a lot of people working on this type of thing through retrieval augmented generation or like other LLM technologies. But I would say that it still doesn't replace this. You still end up wanting this sort of spreadsheet and be able to manipulate numbers as numbers and to know, like, okay, exactly what samples things are, and to have things as, to work with data essentially. So the ability to have models which understand text doesn't replace the need to have data, and so we end up wanting to map text into data in various ways. The other thing that we really need to do is have data that feeds into programs. So at some point during our pipelines, we want to feed things out of a machine learning model into another program. And those other programs don't speak continuous representations. They don't just speak pure vector. They need symbolic data. They need something extracted. They need some numeric representations. And that's where you end up with doing this type of thing of saying, okay, how do I actually get data fed forward out of some sort of schema? So this breaks down into a number of different subtasks. So here we have like named entity recognition, or recognizing these like spans. Then we do some entity disambiguation to link it to some knowledge base that we have. Often we're looking up into a custom database from this. We're doing little things like currency normalization. And we don't want to do all of these little steps in a large language model either. We want to have some sort of targeted model. So, at least that's the claim, and we'll see about this. So, okay, let's say we recognize that, yes, we need to do these little tasks like named entity recognition, entity extraction, information extraction, etc. Can we just use a large language model? Can we just prompt a large language model and use that as a model itself? How accurate is that compared to other approaches? So I'll skip this in the interest of time, but the point here was just to go through the sort of simplicity of how really early classifiers worked, just like iterating over words, adjusting some values here or there, and training a model that way. So this is just all of the code that you need for a perceptron tagger, and it's the sort of example of how directly and easily you can train a model that does some specific task, and actually you do very well with this for, say, a bag of words model on things like text classification. And the results that I'll show you for the language models, zero-shot learning, actually generally will perform kind of similar or much or worse than this on many of the problems. And I think that's an interesting thing to look at. So, and then finally, as well, I think, if we're talking about these things just sort of conceptually, we should make a distinction when we're talking about large language models. So we can talk about something where we've got a generic objective. So we're just like, a language model objective, like, as a large language model has, and very little task data. So this is the zero-shot or few-shot in-context learning. Or we can say we've got a generic objective and some task data. So this is the style of fine-tuning where you throw some data at like OpenAI and you're able to like sort of learn a little bit on your task, but you're still approaching it as a task of sort of prompting. And then next, in this quadrant, we've got nothing. Here we can say, all right, if we have a task-specific objective and task-specific data. So there we're learning like a custom named entity recognition model or like a custom text classification model. And it's really that we're training an objective function that maps exactly to that task. So we've got some like output vector and, we're training a negative log likelihood of that or something like that. So what I'm going to be comparing it is first and fourth quadrant. So I'm not talking about fine-tuning in the sense of, fine-tuning an LLM where it's still in this sort of question and answer format, but you're giving it some data that's more like the types of tasks that you're doing. I'm talking specifically about something like, okay, we'll initialize some weights with like BERT or something like that and train a model that's specific to that task and has a task-specific objective. And contrasting that with zero few-shot learning that you're just engaging in via a prompt. Okay, so with that, all of that set up, how does this actually map out? So here's one set of results on this task of named entity recognition where you're, looking at, say, just these recognizing spans of, say, person, organization, etc. So this is from a recent paper that was published by some researchers at CMU, and they're comparing GPT 3.5, GPT4 against Spacey, Flare, the current state of the art here, and then also the state of the art from 2003. So what we see here is that GPT 3.5 and GPT4 perform actually surprisingly poorly at this simple task on this data set. So it only has 4 classes to learn, organization, person, location, etc. And even more, GPT4 actually has seen ample descriptions of this task and this benchmark actually in its training data. So you can query GPT-4 about this task and it knows all about what it's supposed to do. So it's not even a true zero-shot task in that sense. It has this knowledge of what you're referring to if you tell it that you want to do this. And yet it still only gets this 84%, which is worse than the state-of-the-art accuracy in 2003. And significantly worse than smaller models that we produce with Spacey, and then the state-of-the-art accuracies around this are like 94 or 95. So this is surprising because this task seems so simple, and yet the models again perform like surprisingly poorly at it. So this is just one data point, but it's already all right. So what's going on here? Let's look at some other data as well. So this paper goes through an enormous range of experiments. This one doesn't go through GPT-4. But it does go the range of GPT-3 models from OpenAI, and it evaluates them on data sets across text classification, part-of-speech tagging, entity recognition, etc. And I won't go through the table here, but the broad picture here is that on all of these tasks, the accuracy is significantly below what you get from this current state-of-the-art, which again is interesting. And not only the current state-of-the-art, but state-of-the-art from years ago. Like this would be outperform the pre-neural models, would do better than these than the LLMs on these tasks. So and then this paper is a bit of a counterpoint. This one got a lot of traction across social media, but it's actually kind of an outlier versus the other results. So this one found that crowd workers, workers on Mechanical Turk, etc., do worse than just putting the model into GPT-4 or ChatGPT on these tasks. So one of the things to think about here is when you a lot of people there were a lot of sort of blog headlines about this of like ChatGPT doing better than humans on these tasks. But if you think about it, it's like a slightly interesting thing because the gold standard you're comparing to there is human annotation. Like that's the truth that you're like evaluating both the crowd workers and the GPT4 against. So it's weird to say that it does better than humans when like, humans are that gold standard. So I think that actually, if you look at again, there's too many results here to go through in detail, but across the board, the accuracies here are also quite low. And so I think this is more saying that like they got quite poor accuracy out of their crowd workers. And that's definitely something that's possible to do. It's very possible to get not very good accuracy out of crowd workers on tasks like named entity recognition, text classification, etc. So I see this as more around that rather than concluding that the models are especially good at these tasks already. And if you tried to conclude from this that like, hey, okay, I don't need human annotation, what I need is just the LLM, you end up like quite disappointed because you then find that there's no way to actually get the accuracy that you would have gotten if you just had a good annotation process and trained the task-specific model instead. So, and then another paper here, this was a great paper from Microsoft that did a huge amount of experimentation on named entity recognition with their own models. So the innovation in this paper is training a model that's specifically supposed to be good at few or zero-shot NER. So this is a model that's kind of in this quadrant 2 of the graph before, where it's still a large language model and it's still like, it being interacted with via a prompt, but they've given it examples that make it better at like solving NER tasks in general. So this is a 7 billion parameter model that greatly outperforms ChatGPT and other larger models at this task of few-shot NER. Then you can also go forward from here and train it on specific tasks. They find that they still find that BERT-based is competitive in many of these ways even after doing the supervision, some task supervision, but it's still like a great step forward. And I think actually this is more what it will look like to start using large language models in these ways, to start training them specifically for zero or few-shot learning. And another thing that we can see from this general picture is, again, ChatGPT is performing poorly on this. So I'm trying to build this general picture of like, okay, it's not just one or two data sets. There's a general pattern across the literature of the large language models performing surprisingly poorly on predictive tasks. Then we did a few examples ourselves. These are kind of limited. We did this on GPT-3. So here we're asking this sort of data ablation question of, okay, if we take away a lot of data, how do we actually do? And we actually went into this research project around this, assuming that the large language models would do much better than they did. We thought, okay, we'll be able to save some time and just use the large language models as this annotation augmentation, maybe use them to distill a smaller model. And instead what we found was that the accuracies out of the box on the large language models were surprisingly poor. So this is one data set where the large language model actually does quite well. So this is a sentiment analysis tree bank. It has to predict positive or negative. And here on movie reviews, so this is a data set that's comparatively easy. And it has two features that I think make it particularly the large language model zero-shot learning particularly good at this. So one is that it's got a task definition that the large language model has seen before. Sentiment analysis is a common task. Again, you can ask ChatGPT what sentiment analysis is or what it should do for positive or negative movie reviews. You can ask it to generate a positive movie review, and it will understand this very well. And so, again, in a sense, it's not really a zero-shot task. It's not learning something that it didn't have any idea about from its training data. It's understood this general task from the training data, and it's able to perform it. So here it gets like 94%, and we have to use quite a bit of the training data to get to a similar accuracy. So this is a success story for the zero-shot learning. Although, again, with speed, it's not nearly as good as the smaller model. However, on another fairly simple task of classifying news articles into different categories, here we only need to use like 1% of the data, and we're already like greatly outperforming the ChatGPT baseline. So this has some features which are much harder for zero-shot or few-shot learning. One is that there's just a lot of classes. So the more classes you have, the harder it is for the model to sort of pick apart this task. So with 20 text classes, that's something which, if you're just training a model, it's not a big deal to have more classes. But if you're doing few-shot learning, then it's really difficult because you have to have exemplars for all of these tasks. Another thing is that the examples in the text are not so short. And this means if you think about like few-shot learning, you're giving it an example of what that label is. Well, every one of those examples, if that's a 400-word article, that's like a lot of distraction in the prompt. And it's just a lot of extra information. So then you end up having to play tricks like, okay, can I summarize this article? How can I distill this information? And a lot of the time when people are saying these zero-shot tasks, they're imagining it as like a sentence. But often for text classification, well, it's not a sentence. It's like, an article. And then giving like a whole article in a prompt is actually quite difficult, especially as you go for 20. If you're saying, well, I want two examples per class, and then you've got 20 classes, and each article is 300 words, which even isn't that long in a text, suddenly your prompts are enormous. And you can see how it's quite difficult technically. And then finally, on this last task, this one has 77 classes. And so here again, we pack in like, a few examples per prompt. Like the prompts get massive. We couldn't, and at the end of it, it still doesn't perform very well. And if we have even 5% of the data, we're already doing much better with a small model. So here for this, I wanted to do some examples where, some experiments where I tested specifically, okay, exactly how many examples do I need to beat GPT-4? And the problem that I had was that actually when I used GPT-4, it kept timing out. And so I've used Claude 2, which is a similar size and accuracy model for this. And I used a data set called FabNER. So this is just another data set that was on Hugging Face data sets. This one's on machine manuals, so it's a sort of specialist literature. And I wanted to do this because I wanted a task which wasn't just something that it had seen before. And so it's recognizing these categories. And actually on this, the Claude 2 and GPT-3 also perform similar at about 18%. From the limited amount I got from GPT-4, it was a little bit better, about 30%. But we're already doing better from a CNN model with only 20 examples because the baseline accuracy here is very low. And again, this is only one experiment, but it's consistent with what we've seen in the rest of the literature that it's surprisingly poor on these type of tasks. So, all right. How should we think about this? What should we do? Like, the answer shouldn't be, well, okay, like we're actually no further forward from large language models than we were before on these predictive tasks, because there is a lot that we can do with them. It's just that what we shouldn't do is say, well, let's just use the large language model as a classifier. That's not a good use of the model. It's extremely expensive. It's high latency. And the results that you'll get are worse than you were getting before. And in fact, even the sort of fast start advantage of saying like, well, I don't need to label data. You need so few labeled examples that the amount of faffing around you'll do with the prompts and stuff is actually more work than actually just labeling examples. And it's less reliable work, the faffing around with prompts, whereas the improvement that you get for doing the annotation is actually quite consistent, and you can plan for it. Like, all right, if I label like 1,000 examples of this, I'll probably do pretty well, because using like language model initialization, models like BERT are actually very sample efficient. So the way that I think we should think about this is abstract the whole problem as thinking about having all of these different computational devices that we can schedule work to or allocate work to. And this includes like a human as a computational device. So like, you can see humans as some hardware that you can send the problem to and get back an answer. And similarly, LLMs are another type of device that you can send the problem to and get back an answer. And if you think about it this way, we're already kind of used to having CPU and GPU and having to arrange computation differently between them, and having situations where actually it's advantageous to use CPU here versus GPU, using CPUs to compile your data or arrange your data in a way that's more friendly for execution on like the more expensive device. Well, both humans and LLMs are like this, but more so, and have very particular characteristics. So humans and LLMs are also more they're higher latency, but if you're sending a device to a human, you also want to pay attention to like the working memory and not overload, how you not overload that working memory and see it through. So I'll show you this in a little bit. So here, this is a little workflow with our tool Prodigy is just an example of, a sort of sketch of what this can look like. So we can write programs that very flexibly work through our examples and queue up the data in different ways. So we can say, and then we can get feedback from the human and use that to update the model in the loop or update things. So the sketch here is, we're loading things up with an LLM, we're generating examples from the stream, and then we're updating the model in the loop from as we're getting examples back. And from this, we're able to more effectively queue up tasks for the human and use that device more efficiently. And in particular, and this applies as well to an LLM. So if it turns out that, okay, we can't easily have an LLM few-shot learn over 20 labels, well, let's change the task around and ask one label at a time, or let's use the LLM as another annotator in conjunction with a human and say, where did they disagree, and then have somebody adjudicate that. Through all of these things, like, using it as a different source of information and a different device that we can allocate work to, we'll be able to more effectively create data assets and essentially compile information that then will make our program. So yeah. So again, in summary, if we're thinking about this as scheduling computation on humans, well, a human has a very high latency. You can't switch tasks immediately. You've got to take some time to boot up and get into what you're doing, right? And then another really important principle for using annotation efficiently is what we like to say, don't thrash the cache. So if you've got some task with again, a bunch of labels, it feels really bad to people to have humans annotate the same example many times, but it's much better to go over the same example many times with a simple annotation scheme than to have a loop that goes, okay, I'll take this data set and then I will page through this really complex annotation manual in my mind and try exhaustively to annotate everything on this one sample. Because the loop that you're doing mentally there and the load on your working memory is really high. Whereas if you're doing a really simple task of, say, one label, you can fly through it because you're just seeing the thing, recognize the pattern. And so it doesn't matter if you're looping through the data many times, if you're arranging the computation efficiently so that people are able to stay in the zone, stay focused, and make quick decisions and not fret that they're forgetting things, then you're able to actually make use of that much more efficiently. And the same will be true with LLMs, and you can have different ways of using LLMs to arrange computation so that you're getting the most out of all of these devices. And the end goal of all of this is to say, all right, we want to have a program that recognizes these things. Maybe this is actually quite easy. We can create these data assets and compile a simple model. So we can use all of this as compilation rather than as the program itself. Thanks.